We welcome Sigrid Adriaenssens.
No, this is working well. Well, first of all, Doris, thank you for the very nice introduction. I'm very happy to be here today, and I had the pleasure this afternoon to be in some of your studios, and I'm very impressed with how structure is very much already in your work. I'm very impressed with the work that you do. About 15 years ago, I moved my family from Belgium, originally from Belgium, to New Jersey, because residence in New Jersey. And in the beginning, we have to go to the seashore. And this is route one. This is the I did go to the beach. And I always struck. Hello? Yeah, I think that's better. Yeah, that's good. So I'm always a bit shocked by when I see these bridges, because the construction industry is one of the most resource intensive industries. And I kind of learned when I was at university that if you want to design a bridge according to the forces that are in it, you would kind of design it like this. And this is the sketch. And you see there is about 30% less material in this. Of course, that means that the bridge would be cheaper, but also it would mean that it would have smaller carbon footprint. Then when we get to the shore on the East Coast, this is kind of what this looks like. This is actually not the New Jersey shore, this is Rockaway Peninsula, and I'll talk about that. So this is very close to New York. So we see a lot of people having fun, but actually we see a lot of people, and we also see that the buildings are very close to the seafront. And as you know, the population is going to grow a lot by 2050, and we're going to need about 65% increase of floor space. So that's good for us, architects and structural engineers, but we have some challenges. First of all, what you see here is a diagram that shows, on the one hand, labor productivity, and then it also shows ODs. And so you see basically the United States and the construction industry is the line that is kind of at the bottom. This is from McKinsey report. So over the years, the productivity of the site has gone down. And actually, if you look on site today, actually there's a lot of construction sites here on campus, you see that the practices are not that innovative, right? Like if you imagine a construction site 50 years ago, it would look very similar. Maybe the person wouldn't be wearing helmets, but it looks very similar. Similarly, also, we use a lot of materials that are non-renewable, right? We use about 40%, I say we are in the construction industry, so that's both you and the engineers and the contractors, right? We use about 40% of the global non-renewable resources. So, for example, if you think about sand, which is a component that is very much needed in concrete, that is today a commodity that is quite easily, but it's estimated that very soon this will be not so available anymore. Also, the construction industry produces a lot of waste. In the United States, it's about 29% of the landfill, and that is, of course, not very good. Also, we produce in the making of the materials a lot of CO2 emissions. We're responsible for about 30% of the CO2 emissions, and that caused in China in 2017, the construction sites had to be closed because there was just too much pollution going on. And then finally, not only are we kind of adding to the problem of climate change, we actually also have to design for it. And for me, this is very shocking, because when I was at school a very long time ago, we just took the loads from the code. But now these loads are changing a lot. And the picture that you see here is not a rendering. It's a picture from Hurricane Sandy, which hit the shore where I live about in 2012. So we had a very big hurricane, because these houses are close to the beach. There was a lot of damage, not only financial damage, but also social damage. And so we have to design for heavier loads, whether these are loads are induced due to climate change, like here these are hurricanes, or whether these are due to loads, man-made loads. But what happened in New Jersey after the hurricane hit, most of the communities rebuilt their boardwalks, very quickly after the storm, just like they were before. So basically, they didn't do any kind of mitigation scheme, or they didn't really think about that this storm might happen again. They just rebuilt the boardwalk and get the finances to do that. But of course, that is a disaster waiting to happen again. Or in other cases, like this one here, this is Sigrid. It is also a town in New Jersey. Their solution was to build a big stone wall. The idea here is that if you put a lot of land, so if you put a lot of stones, the stones will stop the force of the hurricane. Of course, what does it bring along is that you cannot actually go on the beach anymore. Also, animals cannot really go from the sea onto the land, and your real estate value goes down. So I don't really think that using mass, so using a lot of stones, a lot of rocks, a lot of concrete, a lot of steel, that's really the solution. So I think that we need to change what we design for, how we design, and how we build. And I advocate, as I have a principle with fortifying lab. So we look at slender surfaces, so how can shells, membranes, nets, how can they maybe solve some of these problems? And we look at how they interact with extreme loading, whether that is earthquakes or whether it's storm surge loading. And how we do that is not by using math, but we use geometry and mechanics to our advantage. And I think we should also start looking at the way we build, because there's so much construction waste going on. So I'm interested in self-assembling processes, and I will talk about these systems But I am not the first person to use form in construction, right? You see here a graph with on the x-axis time and on the y-axis weight. Notice that that's a logarithmic scale. And I have put there some of the more important architecture that has used forms. At the top we have the pyramids, those are of course very solid, very heavy. But along that you also find the Sophia cupola, you find the Gothic cathedrals, you find the Pantheon. And you see that this line it's a linear line, right? If you plot time versus weight. And in the rectangle there, you see the kind of close-up of structures that are actually very, very lightweight. And actually, we were talking today in studio about the roofs, the canopies that are on top of the roofs. If you don't make them heavy enough, or you don't design them well enough, they can actually be uplifted by wind. And so the two structures that we see here at the bottom, they are so lightweight that if you don't design them well, they can actually be uplifted. So I'm not the first one to use form to resist forces, and we are already designing very lightweight structures. I'm going to now show a project that dates back from the time I was working in practice for main partners. We were invited to design a roof over this building. This building is the Dutch Marine Museum. It is a masonry building from the 17th century, when it was a gunpowder house. So the Dutch would stock up here and then go with their boats and explore the world. After it was a gunpowder house, it became a prison because it has so small windows, and then it became a museum. And so when they were renovating the museum, the architect who was renovating the museum convinced the client that they needed a roof, because actually it's not one building, it's 4 buildings. So it's basically, it has a courtyard in the middle, and that courtyard was open to the elements, so it would be raining there and whatever. And so the architect thought it would be great if that space, if we could make a lightweight roof that could rest on the building, not appear above the building, because you're working in a historic context, and then we could use this space for events or for selling tickets or for programs. Now, inside the museum, they exhibited maps and scale models of boats, because the museum is all dedicated to the Dutch history of the 16th and 17th century, when they were doing a lot of seafaring. And so in the museum, we found this map, which is a map that the Dutch produced in the 16th century, depicting what they thought the world would look like. So they've got some parts, right, apart from the United States, is not very rare. But on top of this map, you see that there is also a grid equals, right? So there are actually 16 points, and these 16 points are all connected together. The Dutch thought that those were wind drones. So they thought that the winds were originating from these points and then radiating out to the other points. So they would use these lines as a kind of GPS system. They would sail along these lines as a kind of map to wherever they want to go. So we thought that was an interesting geometric pattern. So we extracted that pattern and thought it would be interesting if we, for the roof, create some kind of steel grid shell with a transparent glass roof that has this pattern in it. So we extracted it and imagined it in plan view on top of the building like this. Of course, as we've been talking today in the studio, you can, so the courtyard measures about 90 by 90 feet. You cannot span that with beams, that's too large distance. So we could not make this a planar structure, or we would have to design it very deep. So we imagined how could this be designed as a kind of a cupola. And so what you see on top is again the same geometry extracted. And then I was very lucky, I just finished my PhD. We used algorithms that I developed during my PhD to model this planar structure as a spring system, like a network of springs. So if you imagine every line to be a spring, and at the node intersections we put a load which represents the self-weight, and then we get this kind of hanging chain model, like a hammer. It was Robert Hooke who said that if you have a hanging chain and you invert it, or if you have a hanging chain network and you invert it, you end up with a perfect cupola. And so, because we use this profiling technique, all the members in that system could be designed very, very thin. A few years fast forward, this we won the competition. This roof was built. Here you see it. It doesn't come above the ridge of the museum because it's in historic context. It was not allowed to be seen from the outside. And this is what it looks like on the inside. So I hope that you recognize, first of all, that you recognize the pattern on the map, but also that you see how thin all these elements are. And that is really because the shape, this curved cupola shape, was found using this form finding method. The other thing that we did is at the nodes of these of the grid, we put in LED lights, so at night it looks like this. And the idea was that maybe then it kind of looks like you're looking at a starry sky. But so while working on this project, I realized that these kind of grid shells and shell structures are actually really good. First of all, they are indeterminate structures. That means that if one of the members breaks for some reason, or if there's a hole somewhere, then the forces will find another path, right? So there's redundancy in the system, and that's generally good. Secondly, there is shell behavior. That's a little bit like the eggs of birds. That means that if you design the right form, you can actually make your members or your thickness very small. And that is because they are mostly loaded in actual loading and bending. And secondly, like shells, also shells on the beach, they are very stiff because of the form, not because there's a lot of mass there, but because they are curvature produce stiffness. We call that geometric stiffness. So all these seem to be really good things. So because of the form, you get all these things kind of for free. Now, I do want to point out, and I think I've said this also in one of the studios, and I say this because in other disciplines where they design stuff, like for example, when you design an iPhone or you design shoes or something, you don't have the challenges that we have at this scale. First is the scale, right? We design always at a very large scale, let's say 10 meters or 100 meters or maybe 1 kilometer for designing a bridge. And it was already Galileo said that, if you take a bone of an animal and you make it like twice or 3 times bigger, you don't just scale it up because area and volume don't scale to the same ratio, right? So there is a limit to how big things we can make. The second thing that we have to deal with in the built environment is time. The things we design are not supposed to last 2 years or like 5 years. They're supposed to last, well, hopefully 50 years, 100 years, 200 years, 2,000 years. So we have to design things that are going to withstand all the, in our case, loading that can occur during that time. And I'm showing here the dome in Florence, which is a masonry dome. I'll talk about that dome later, but which has withstood time, but not only time, it has withstood all the earthquakes in Italy. And then the third challenge that we are confronted with is that we don't have the whole palette of materials that are available. If you look at nature, there are so many materials that nature can use, but because we are building on a large scale and because we have to design things that are very durable, the amount of materials that we can design with is limited. So my research focuses on resilient and sustainable standard structural surfaces. That means forms that are dictated by the forces that are within it. Because of that, they can be very thin. And if they can be very thin, we don't have to use a lot of material, which means that the carbon footprint is smaller. And if we kind of build them and construct them in the right way, they're also more economical. I'm going to be showing 4 projects. I'm going to be talking, and also these kind of structures, these like shells and rings and membranes, they have properties that other structures like beam and column structures cannot have. And it's all due to either their form or due to, I've not talked about this that much, about their topology, means the way that the different nodes are connected to each other. So I'm going to show 4 projects. The first one is I'm going to show how you can use flexible shells to change shape and amplify motion. I'm going to show the second one is about pressurized membranes, how they can actually, how you can change their stiffness. The third one is about nets, and the fourth one is about rigid bridges. So I'm talking about soft flexible systems, some semi-flexible systems, and some rigid systems. So last one is about rigid systems, how we can through the form really give them incredible low capacity, as well as if we think about how to construct them, we can actually construct without form. So first we're going to talk about flexible shells and shape morphing. So so we were looking at the time there was a lot of research also. Professor Sum is doing a lot of research and is really the expert in adaptive facades. So the idea about adaptive facades is that if you can control the aperture of facade, so if you can control how much light and heat comes in, then you can really reduce the building energy bill over building. So this is a rendering of fictitious museum in Marfa, Texas. And this is maybe the same building in the morning if we don't really want that much light. So we started working with the biologists to identify how plants move. Now you think maybe plants don't move like they have to, but actually plants move to pollinate, to get food. And there's actually 5 methods that they move. The first one is differential expansion. It means that you have cells, 2 layers of cells, 1 layer of cells swells, and because of that, you kind of get bending. That's the first one. The second one is torsional buckling. So that are very slender elements. When you put a load on them, they will actually start twisting. The third one is layered material anisotropy. So that's got to do with fiber orientation. So if you put different fibers in different orientations, and then you actuate them through humidity, they will actually start twisting or warping. The last one is release of electric energy, and the one that's most interesting to us is shell geology, like the one that you find in Venus flytrap, right? So the Venus flytrap is a shell. Once there are like little sensors on there, once the plant senses that there is a fly, it actually inverts its curvature and traps the fly, and then eventually eats it. So, and that happens because this bending of the shells is actually comparable to the stretching of the shells. Now, we looked at many plants that exhibit this kind of shell mechanics. We did not go with the Venus flytrap because that's a completely uncontrolled movement, that's like completely open or completely closed. But we found another plant, an Australian plant, called the Stellinium graminifolia, which is shown there on the left-hand side, which uses a kind of mechanism, or less deforming mechanism, to pollinate. And you see on the left-hand side, there is a pink thing that is the active part that does change shape, and then the blue part is the passive part that doesn't really change shape. And so we discovered that the pink part is actually the geometry of the border of a torus.
And as you see there in the pictures in the middle, that's actually the geometry that we find in the Coke bubbles. If you press that just a little bit in the middle, this thing opens up widely. So that's the kind of geometry that we found in the plant. And so we started imagining how could we maybe make like a shell shading device that has an actuator which is based on this torus, and then a passive lip that kind of lifts up. Because for the shading device, this thing either needed to lift up or it needed to twist. And so imagine how we would put like two smart memory on the wires, and then we could either hit them up at the same time, which would lift the lip, or just kind of activate one, which would shorten one of them, and that would cause twisting of the top. And of course, we were looking at plants, but actually we also found that somebody had said that when the shell is thin enough and is vibrating in one of the great possible modes, the middle surface behaves as if it were inextensible. So what does this mean? This means that if you have a very thin geometry and you look at the frequencies that it likes to vibrate in, then you can actually identify surfaces that do not stretch, but that actually bend or twist. And we started using that rather than the kind of biomimetic inspiration as a way to identify these kind of actuators that will open and close, well, lift, bend, and twist. And so we imagine this in adaptive facade. So this is when the twisted, fully open, twisted, fully open, and half open. So that was using flexible shells, smaller scale, because the flexible shells, if you go beyond 1 meter, gravity really starts playing a role, and these things just kind of start drooping. So that works on the smaller scale. And I'm going to talk about really flexible systems nets. In 2015, I received a phone call from Professor Adi at the University of Réunion, which is in the Indian Ocean next to Madagascar. Réunion is a beautiful island. A lot of people go there for tourism, more specifically, they go there for surfing. And Réunion had a few shark attacks, because climate change, the sharks can go different places. And so their tourism was going way down. So the local government had decided to put shark nets on the, and you see the picture in the background that are these shark nets. So this is a plan view of where they install the shark nets. This is in Saint Paul, this is the capital of Réunion. And the green line is the shark net, and on the right-hand side, you see what the shark net will look like. Now, these are all like home depot materials, right? You have like the anchor chain, you have some buoys, and then you have polypropylene, 40 centimeters. That mesh size was determined so that the turtles can still go through it, but not the sharks. So this net, although it all looks like very homemade, was super expensive to install and maintain, super expensive to install because it needs to be installed by scuba divers and on the ocean floor. So there's not really a foundation or something, you just have to put it in the ocean floor. And it's very expensive to maintain because scuba divers every day have to scuba dive along to see whether the net is still intact. These nets lasted about 3 months and then they were broken. So this is on the left-hand side, in the background, you see a video of what it's like for these nets. This is not when there's a cyclone, this is not at high tide, this is like normal kind of conditions because it's in the wave break zone. This looks like a washing machine, right? I had the intuition that these nets, that the topology, so the way that the nodes are connected is not correct. So basically, you recognize the orthogonal one, that is kind of what they had installed. And so we kind of developed models to study the interaction between the nets and the waves. Here you see waves going from left to right, but we also have models with waves going from all kinds of directions. What you see clearly on the left-hand side is that when the water goes up above the net, and this is just the tide, right? The net cannot really extend a lot. And if the net cannot really extend a lot, the tensions in all these cables, in all the vertical cables, becomes very high. Whereas if you have, for example, an hexagonal net, or if you put the orthogonal net at 45 degrees, then that net can extend a lot. The tensions in the vertical bars are much smaller. And these forces, especially in the orthogonal one, you know, the net didn't break from just about one time being tension, but there is something called fatigue. That it happens if you, for example, the can like this one here, if I want to open it, I just open it like this, but if I do 10 times like this thing will go off. I haven't exerted all the force of it, but it's because it's repeated cycles of stress on, stress off, stress on, stress off, I can actually break something. And so that is what happened in this net, I think, combined with maybe grains of sand that are kind of rubbing, that kind of broke these nets. So we studied many different kinds of net topologies, and you see from all the waves coming from different directions, and you see they all behave kind of the same, except for one, there's really one outlier, the blue one, and that's the one that builds, right? So they built from all the possible combinations, they built the worst net, and of course they grow after 3 months. Now, because of my expertise in nets and the modeling of nets, I was approached by a choreographer called Rebecca Lazier and a visual artist called Jonathan Eckelman. The two of them had started a collaboration to see how they could make a choreographic piece where the net becomes like a dancer. So here, the requirements for the nets are to be as expressive as possible, or also so that the dancers can have control over the stiffness of the net. So I'm still working with them today to kind of study how typology, so on the left-hand side here, you have the orthogonal topology, on the right-hand side here, 45 degrees typology, how topology, the way that we ring things, but also the way that we maybe put stiffening grips in the net, how that all affects the behavior of the net when they're interacting with the dancers. I also around the same time started working on another project that was inspired by lace. So you see there on the top right-hand side, that's lace. So lace is a handicraft. It's not knitting, it's not crocheting. It's a little bit like weaving. So basically you have threads and then you have other threads going around it. But the difference with weaving is that weaving is at 90 degrees to each other. Lace, what this is with many different threads, and they're all at different angles. And we found that if you make these, so usually these pieces are about this big, right? But so we found that if you scale them up and you don't use round diameter thread, so you don't use like cotton thread, but you use a kind of strip, these planar surfaces kind of take on a three-dimensional shape. That's what you see on the left-hand side. And so we kind of figured out that at the smallest unit level, it's because if you have two elements that are not circular, but that have a rectangular section, and you force them at a certain angle to be planar, we call that kind of geometric frustration. They cannot stay in that way, and they actually buckle out of plane. So in the right-hand column, you see one where it's happily staying in plane, but as you start increasing the angle there at 90 degrees, it kind of goes out of plane. And also, if you make the dimension between the thickness and the width very large, then they also buckle out of plane. So then we started putting these things together in rings. And so we found that if you put a number of what we call these bigons together, you can actually create many flexible different shapes. We call these bistable shapes. That means that this shape can be stable in many different configurations. We also started putting them together first in a flat surface, and then kind of switching the bindings going up and down so that we could go from kind of a planar surface to an entirely doubly curved surface. And this is a piece that we made for our exhibition. Okay, now I'm going to talk about shells. So some of you in the third year studio are doing widgets and shells. Shells are just amazing. Here are some pictures of shells, just taken from the internet. And so shells have throughout history proven to be very resilient under earthquakes, tornadoes, hurricanes. And so we wanted to find out why that is. Why are they so good at taking these extreme loadings? So we took this shell as our case study. This is Felix Galila Church of Our Miraculous Medal in Mexico. This church, which stood in 1985, there was a huge earthquake in Mexico, like the magnitude was 8. And so we took this geometry and carried out all kinds of analysis to kind of study, like what are the under that earthquake, what are the forces, and so what we see is that the stresses are all quite low. But the thing that was very surprising is when we looked at what we call the eigenfrequency. So the eigenfrequency of the structure is the frequency at which a structure likes to start, shaking about. And what we found for the shell is that the eigenfrequency is very high. The value is 3.09 hertz or higher, because there's more than one eigenfrequency. And the frequency of the earthquake is much lower. It's more in the order of 0.5. So the frequency of the earthquake means like how often it hits in a certain time period, and the eigenfrequency of the structure are very far remote from each other. And that, as a consequence, you don't really get a lot of structural damage, because when these two frequencies, so the frequency of the earthquake and the frequency of the structure coincide, we get what we call resonance, and then the structure starts moving about much bigger, and you get structural damage. You might have seen some other examples, or for example, the Millennium Bridge. I remember in 2000 they opened this bridge. There were so many people on the bridge starts shaking in the frequency that it likes. People start adapting their step on it, and then you get resonance, like the whole thing just shakes more and more. So you absolutely want to avoid that. And so these shells have very high eigenfrequencies. And on the left-hand side is the only formula I'm showing. You see the formula for eigenfrequency is the square root of stiffness over mass. Okay, for shells, mass very small, it's very thin. Stiffness very high because it's curved and geometric stiffness. So the eigenfrequency is very high. It's much higher than, for example, for normal frames structures. So that's good. So then we started developing techniques for how can we develop forms for arcs. First starting with arches that can take gravity loading and lateral loading. So we used a method called graphic statics. And we kind of saw that we could develop these lines, these stress lines, that's where all the forces are. And of course, with this earthquake can go from the left or the right. We have mirror imaged the truss lines, and we end up with these kind of weird looking arches that are supposed to be really good under gravity loading and earthquake. And we checked, and they are indeed very resistant to earthquake loading. And maybe quite like when you build an arch with that kind of shape, but actually 3D printing, this is now maybe possible. But we're not so much interested in building arches, we're more interested in building shapes. So instead of just building an arch, we actually offset one of the curves, and then we look like someone we also do a surface surface. So we end up now with this very corrugated surface, and supposedly this is then supposed to be very good for earthquake loading. First of all, you might say, I've never seen a shell like that before. But actually in 1978, Adriaenssens in Uruguay built a corrugated shell like this. This is not an iconic shell, it's not a Frank Gehry shell. It was a shell built as a warehouse to store grains, right? So it's very cheap structure. So that's his structure, that's ours. The difference between his structure, there's many differences between his structure and our structure, but in terms of geometry, in Adriaenssens shells, the corrugations run or continue over the entire surface, whereas with us they're offset, as you can see, they're kind of slightly shifted. So the curvature is slightly different. So then we carried out, we made many models actually in Rhino. So how we do that, when we do parametric studies, we make our models in Rhino, and then we study them using finite element methods. So we made a number of variations of the shell in Rhino, and then we analyzed them in finite element analysis. So the things that we varied, like this Rhino's parametric modeling, so we varied either the correlation depth, so you see some of them have very small correlation depths, some have much larger, and also the periodicity. So that is like how often these waves kind of reoccur. And we carried out this analysis. Basically, we put a horizontal load on it, and then at some point, so we to break this in the reinforced concrete. At some point, the shell starts cracking, but then the program doesn't stop. It keeps on pushing and pushing until the whole shell is cracked and actually fails down. And so all six kind of fail with the same failure mechanism. That means that there are 4 hinges, but the location of the hinges is different. Some of them have like a hinge at the ground, so like for example FF2 has like a cracking zone C, also FF3, but then there's already also FF4, but for example FF5 and FF1 don't have a cracking zone at the top. So we were interested in, so with the geometry, so they all have the same amount of material, but they have different geometries of different corrugation depths and different periodicities. You can actually affect the way that it's going to fail. And it fails in these areas because that are the areas that are singly curved. So in our geometry, most areas are doubly curved, means they're curved in both directions, a bit like a sphere. But there are some areas that are singly curved, means they only have curvature in one direction, like for example, a cylinder. And so the singly curved areas are less stiff, so they are going to deform more, and that's where the cracks start occurring. And so when we compare all these shells, with the DSD shell as a kind of ground model or base model, we see that for the DSD shell, it will start actually collapsing under 0.3 G. That is kind of earthquake design. But all the other shells weigh same amount of volume, just different geometry, way outperformed the DSD shell, and actually the one with FF3 was the one that's so FF3, if you see, has quite a deep corrugation depth, but very small periodicity. And that one, so same amount of volume, just different geometry, is going to fail around 0.58 gigapascal. So much better than the first one. So this was very exciting for me to see that by just changing the corrugations, you can increase the capacity of the shell. So you don't have to add more material, it's just changing the geometry. And here you see a picture or rendering of it imagined in the urban context. But so people don't build shells anymore, right? They don't build concrete shells anymore, although they're very efficient. And that is, according to a survey of contractors, is because it's very expensive to build them, because you have to first build scaffolding and formwork, and then you cast the shell on top of it, and then you remove the formwork. So it's basically building 2 structures. One is the entire wooden structure underneath to receive it, and then you build the concrete structure. Once that's dry, then you remove the timber structure. So we were interested in how could we build curved surfaces without any formwork at all. I'll go back to this slide here. I talked about this dome before. This is the Santa Maria del Fiore in Florence. It was, I don't know if you noticed it. So it was a design competition. There was a clock maker, his name is Filippo Brunelleschi. He entered and he won the competition, and he said he was going to build this without formwork, because this is in Tuscany. There would not be enough trees, or not any trees left, if they were going to cut down all the trees to build the formwork for this. So in manuscripts, we have found that Brunelleschi built this without formwork, but actually nobody really knows how this is mechanically possible, right? So we know that he did it. This was, in literature, but actually nobody had figured out how could this be possible. So from that time, there are drawings like the one on the left-hand side. This is a drawing by the Sangalo family. So the Sangalo family was a guild of masons. So they built a lot of Renaissance domes in that area, Italy. And this drawing is from them. So on the left-hand side, we see part of a plan of a dome, a circular dome. And on the right-hand side, we see a cross-section. In the plan, you see 2 things. One, you see these kind of spirals going like this, and you also see the radial line down of the bricks. On the cross section, you see that actually it's a double dome. Double domes are always good for earthquakes. So, as you can imagine, if you can build the first dome, the interior dome, then you can use that as kind of formwork and scaffolding to build the outer dome. So we were just interested in how could he build the inner dome without scaffolding. Obviously, the herringbone, what we call the spiral pattern, we call it the herringbone pattern, is very striking. A lot of people think that this is for aesthetic reasons, but if you go inside this dome, there's a fresco on it. So the herringbone pattern is absolutely not for aesthetic reasons. And so some of the domes, the Renaissance domes, have these kind of single spiraling, and some have like double spiraling, like the rendering that we make here. This is a right on wall, right? Right on the side. So we kind of try to set out how you can construct a dome like that. And we call it a self-balancing dome. That means that some kind of equilibrium emerges because of the interaction between all the bricks. So we assume two things. First of all, we assume that these domes were built immediately, like in igloo, in pizza slices, which is round and round and round. And then we also assume that they were kind of, at some point, first you build them and they're a bit like building walls, and then eventually it starts curving inwards. So we also assume there was some kind of curving inwards going on. So first you start building, the dome is quite vertical, so it's like a little bit like building a pool, but then at some point, you're starting to curve inwards. And what happens then is very interesting. So these, what we call herringbone bricks, these gray, dark gray bricks, which are stuck vertically like this. What happens is when the mason puts down these bricks here, they want to start sliding inwards, but then they kind of collide with these vertical bricks, a bit like book stands, and they jump against that, and then the domes slide inwards. So when you see here now on the right-hand side, it's still from a discrete element modeling. So we basically make models with like putting all these bricks and then doing analysis, and putting another brick, doing analysis, doing another brick, and doing analysis. And so what you see there on the right-hand side, on the top is if you assume that there is no friction in this system. So basically, if all your bricks would be Teflon coated, then these bricks would start sliding inwards. But from the moment that you have some friction, and actually some friction means 10%, but in reality, if you have bricks in water, it's more like 20 to 30%. If you have some friction, then these bricks, when they want to start sliding inwards, they kind of collide against the outer bricks, and then the outer bricks then transfer the forces to the layer below, and then those to the layer below, etc., etc. And so in that way, you can actually construct a dome all the way up without using any scaffolding or support. Of course, you would need some scaffolding to have your people there for the masons, but structurally speaking, or mechanically speaking, you don't need any external support. And so this is very interesting to me. But of course, it's interesting to study how historic structures were, but it's really only interesting if you can understand what is the algorithm and how can we now use this to build structures today. So, how could we use drones, or how could we use robots to build these kind of complex curved surfaces that are always in compression and that don't need any scaffolding. And so we teamed up with I'm going to show a video here, SOM, to build a glass brick vault. They were exploring how you can actually use digital technologies to build more efficiently or with less risk. So the idea is that we can build this thing with robot-human interaction. The robots are there to do two things. One is to place a brick. And the wonderful thing about robots is that they can place, often they are used for just repeating the same task, but they can do more than that. They have incredible accurate geometry precision, so they can put a brick exactly in the right place, so they're perfect for making complex geometries. And they can also hold a brick for a long time in space. And mason cannot hold a brick for a long time in space like this. And they can also have a certain load capacity, so they can actually support it. So we chose glass bricks to work with, because that kind of emphasize. People think that those are very fragile kind of elements, but actually very strong. So we used, or we're actually dating the form finding for the vault, and we were involved with studying the sequencing and the patterning of the bricks, so that, as you can see here, there is no formwork at all, and the robot is working together with PhD student, I think just an effort to complete this entire vault. So no temporary supports whatsoever, no waste, no construction waste, only humans and robots working together, putting these bricks in the right place. Okay, I'm coming now, well, kind of close a circle. I'm going to talk about pressurized membranes. So these are very flexible membranes. They don't have any stiffness. If you don't do anything with them, they will just kind of flop down. And they can only be loaded in tension, right? If you put the compression in them, they will just like wrinkle. And so I'm going back to this idea of how are we going to adapt to climate change. And as I mentioned before, one solution would be we build big walls, use a lot of salt or a lot of concrete, and then we kind of hope that all that mass of material is going to stop the very strong waves that come along with a hurricane. So I was thinking, well, we don't really need these seawalls always. We only need them when there is a storm surge warning. So I started imagining, could we have a deployable system? And in this rendering, you see these kind of like wavy balloons there. So I started imagining, could we have like a pressurized membrane that could be, when there is no storm, which is most of the time, it can be stowed away under the boardwalk. And when the storm surge warning comes, these systems can be pressurized in a day, and they can form a barrier against extreme loading of storm surges. Now, this technique of using inflated membranes to kind of control water has been used before in dam technology, but those are much smaller and the loads are much smaller. It's just static water, just saying water. So we kind of started this again for, I showed that picture before. This is Rockaway Peninsula in Queens, in New York. And so I started imagining what, because that area suffered from a lot of damage during Hurricane Sandy. And we also had measurements of how high the water had to come during Hurricane Sandy. So imagine if you have a storm surge barrier there that's inflatable. And so, so the scale is very big, right? It's 8 to 10 meters diameter. The loads are very big. We have three kinds of loads. The first load is hydrostatic load, so that's just the water that sits there. The other one is the hydrodynamic load, which is just the waves going on and off and on and off. And then the third load is the wave break load. That's the same one that we saw in the nets, right? This is the waves crushing on the barrier. Because this barrier is flexible, it will deform under these loads. Actually, it will deform really a lot. So we developed a whole fluid structure interaction model to study, for example, how under the loading or the heights that were experienced with Hurricane Sandy, how this balloon would kind of deform, how it would be stressed, and also whether there would be any resonance. And so we actually found that it behaved very well. On the right-hand side, you see kind of an engineering proof of concept of how this would be, right? So this balloon would be this the dotted line. That's where it would be under the boardwalk. And then it would be the storms coming, the boardwalk would be on that. The balloon would be inflated. Of course, you need a huge foundation because this balloon can lift off. So you need to keep the balloon down. And you have to, of course, also keep this membrane tensioned at all times. If I, as I mentioned before, if you have a rope and press together, it becomes very confident. It doesn't have any structural capacity. So you have to make sure that the thing is pressured all the time under all these kind of loading conditions. And you have to kind of check for three things. One, you have to make sure that the water, and it doesn't deform so much that the water is going over. The second one you have to check is that the stresses, that it's strong enough, that the stresses that occur are well within the range. And then the third one is also the resonance. Right? You have here the waves that are hitting it all the time, and you also have some kind of vibration that the structure likes to do. So you have to make sure that these two things are also very separate. And so again, the same thing as what we found with the nets is that you can actually control the stiffness of this balloon, so how much is going to deform with the pressure that you're putting on it. So the loading that you put on it, in this case, the pressure, you can actually make this balloon stiffer. It's just like blowing in a balloon, right? If you blow a lot in it, it will become quite stiff. If you leave a lot of air out, the pressure is very low, it becomes very flexible. And so this can also be used for these very large scale storm surge barriers. And so we kind of proven that these kind of barriers are feasible at that kind of scale. And that kind of brings me to the end of my presentation. So I hope that I've been able to show how in these slender surfaces, whether they are membranes or flexible shells or nets or solid shells, that they have kind of really interesting mechanical properties, right? They can amplify motion, they can stiffen, they can enhance load carrying capacity, and not because there is a lot of material in there, but really because of their geometry, because of the corrugations that you put in it, because of their topology in the case of the nets, like how you connect all the nodes together, that can all affect the mechanical performance of these systems. And so I like to study these kind of systems for applications in the urban environment. I get my inspiration from practices either from art or craft, biology or history. And of course, to study all these systems, we have to develop techniques to study them. So we use machine learning, and we show this in this presentation. But sometimes we use graphical and analytical methodologies to kind of help us understand how these systems work, and once we understand how they work, how we can optimize for data performance. Thank you very much.